Everything you can think of, whether that's a piece of bread or a proton or a lump of star, everything you can think of is either comprised of fermions or bosons. These are the two particles that make up the universe. They are almost the same but different. And in this video, I'm going to outline where these two types of particles come from. Now, these two types of particles behave very similarly but also very differently. And one of them, the fermions, are responsible for basically all of chemistry. The entire field of chemistry comes from one principle, the Pauli exclusion principle, which I'm going to derive later. Fermions include things that are electrons, protons, neutrons, quarks, stuff like that. And bosons are things like photons, phonons, gluons, stuff like that. The thing that differentiates between them is fermions have a spin of 1/2 or any odd multiple of 1/2, and bosons have integer spin of 0, 1, 2, 3. But how do we get to determining these two different types of particles? Well, this is actually a continuation of my videos on statistical physics, and particularly looking at quantum gases. Now, in the last video, which was a while ago, I know, we looked at the dilute gas limit of a classical gas. You use this approximation that the chemical potential, mu, is much, much greater in magnitude than the thermal energy, and from that you can derive the ideal gas equation right here. But in a quantum gas, this is not the case. You find that at certain densities and temperatures, which is governed by the thermal wavelength, which I derived, you actually find that the gas behaves very differently, and you can't use a lot of the classical Maxwell-Boltzmann statistics that you use to predict the gas dynamics. We're going to carry on in this video, and we're going to have a look at how going into this quantum regime of gases creates these two different types of particles that arise from there. So a couple of videos ago, I mentioned this concept of distinguishable and indistinguishable particles, and I'll just go through that again. Let's consider a system where we have two states, and I'm just going to draw these as kind of bowls for now, and these represent the possible states of a particle. Now, I'm going to draw the particles as I'm going to draw one red one, and I'm going to draw a blue particle. Now, this represents two different particles that are at the moment distinguishable. So we're going to now consider the classical case in which particles are in fact distinguishable. So how many different states can we get from this? Well, we can see that our options are, for filling up different bowls, we could either put both particles in one bowl, that's one option. We could put both particles in another bowl, or we could put one particle in each bowl, or we could do the opposite way around, one particle in each bowl, but in the different bowl. So how many states is that? Well, there were 4 when we counted that up. There were 4 different ways of putting both balls in both containers. So that is the case for a distinguishable particle. But what about an indistinguishable particle? Well, if it's indistinguishable, we're going to not see any difference between these two particles. And so to illustrate this, I'm going to draw both as being red. So what's going to happen now when we start filling up states? Well, we're going to have the state in which both particles are in the left bowl. That's 1. We're going to have the state where both particles are in the right bowl, which is 2. And we're now going to have a state where one particle is in each bowl, but unlike before, when we swap the two over, we're not going to see any difference with this time. This is going to be exactly the same. And I swap this particle over here and put this particle in here. There is not going to be any difference between that state than before. So we consider this to be the same state. For all physical properties, it is the exact same state. And that is what we're getting at between the difference between distinguishable and non-distinguishable particles. Now, the quantum effects come when we consider particles as indistinguishable. So this latter case right here is the indistinguishable case. And how we actually describe particles in quantum mechanics is with wave functions. Now, you guys have probably come across the idea of a wave function before. We normally denote wave functions with the symbol psi. Now, this is basically the wave function amplitude of the wave function. It's normally complex valued, but we're just going to plot the real part right here. And basically what it's telling you is what's the probability of finding a particle at a particular location in space or time. We're just going to consider it in space for now, but basically psi is basically saying what's the probability of finding a particle, because of course in quantum mechanics you can never know for sure whether a particle is in a certain position at a certain time. However, you can use probability to describe that. So let's consider two particles just in space. Let's consider these two particles just, somewhere out in the open field. Let's say they're here. What's the wave function going to look like? Well, we're going to see basically two sort of peaks, one right there where the first particle is, and one right there where the second particle is. Now, this is the wave function. I've actually drawn two wave functions right here because there's actually going to be one wave function per particle. So if this is particle 1, this curve right here is the first wave function, and we're going to call that psi 1 of x. And this, likewise, is the second particle, and the second curve is going to be psi 2 of x. Now let's give these positions a name. So let's call this position right here where the first particle is x1, and let's call this position right here x2. So how do we describe the probability of finding both particles, the two-particle wave function? Well, we are going to have our wave function, our combined wave function this time, and it's going to be a function of both x1 and x2. So this is a two-particle wave function. Now I'm going to ask the question, what happens when we swap the particles? What happens when we exchange both particles around? In this example, it's pretty clear to see nothing's going to happen when we swap these two particles around. So what do I actually mean by swap? Well, say both particles, I've kind of drawn them as like Gaussian functions right here. So you have like the first particle being described by a Gaussian, which is going to be something like a constant times e to the minus, that's going to be x minus x1 squared times a constant, which we don't care about. And it's also going to have another constant, so b e to the minus mu, which is another decay constant, e to the minus x2 squared. So your wave function is going to be something like this. It's going to be two Gaussians on the same curve. So what I'm saying is, what happens if we are going to swap x2 and x1? What's going to happen? Well, assuming that a, lambda, b, and mu are all exactly the same, which is kind of how I've drawn it here. A is representing the height of the Gaussian, and lambda is representing how quickly the Gaussian decays to 0. Assuming that they're both the same, nothing's going to change, really. You're going to end up with the exact same formula. So A equals b and lambda equals mu. Then I'll actually just swap these out right here. So that's going to be another a, and that's going to be another lambda. Then if we swap the position of x1 and x2 in the equation, then we're going to get, as I'm sure you guys can probably tell, x minus x2 squared plus a e to the minus lambda x minus x1 squared, which is exactly the same as psi of x1 and x2. So this is what I mean by swapping particles around, particle exchange. I literally mean replace all x1s with x2 and all x2s with x1. The crucial property with this is that when you swap these wave functions, then the only solutions that are valid are ones which basically conserve probability. When I talk about a transformation, of swapping particles, I'm going from psi of x1 and x2 to psi of x2 and x1. So what I'm now imposing is that the probability under particle exchange does not change in the case of indistinguishable particles. So the probability of 1 and 2 is equal to the probability of 2 and 1. Now, what did we say was the relationship between probability and wave function? Well, as you guys hopefully know from quantum mechanics, the probability is equal to the modulus of the wave function squared. So when you do this mathematically, you multiply the wave function by its complex conjugate, and that will give you the probability, which of course has to be a real number, and it's the probability between 0 and 1. This is assuming that the wave function is normalized. If it's not normalized, then you have to go and normalize it such that the probability is equal to 1, because of course the particle has to be found somewhere in space. So this means that if we substitute in psi into this formula right here, then we find that mod psi of x1 x2 squared is equal to mod psi x2 x1 squared. Now, if we take the square root of both sides, we do have to be a little bit careful about doing square roots. Then we find that psi x1 and x2 can give two solutions in terms of the swapped wave function. So you can actually have plus minus psi of x2 and x1, because of course when you square something, if you square a minus sign twice, then that eliminates the minus sign, and so that will obviously lead to both sides of the equation being positive. But when you take the square root, you could in theory have a negative solution for psi. So this part right here is pretty crucial. There are two different solutions, and this is actually the thing that leads to the two different types of particles. So you have one solution where the sign is literally positive, so psi x1 x2 is equal to plus psi x2 and x1, and you have the solution, that's one solution, and you have the solution of psi x1 and x2 is equal to minus psi x2 and x1. So how we technically refer to these two solutions, solution 1 we call the symmetric solution, and solution 2 we call the anti-symmetric solution. And it's kind of got a little bit of a resemblance to odd and even functions. So if you guys have come across odd functions and even functions, then you'll know that cos of x is an even function, and you'll know that if you change x to minus x, taking cosine will not change the final result. Similarly with sine, this is an odd function. The condition for an odd function is that the f of minus x is equal to minus f of x. So basically, if you invert the sign of the argument, then you end up getting the negative overall result, which is the case of sine of x. It's a little bit like that, except in this case, you are swapping not the sign, but you're swapping x1 and x2, and therefore you're getting either the same result or you're getting the same result but multiplied by minus 1. So these two different outcomes for this particle exchange swap lead to fermions and bosons. So the symmetric solution is the boson solution. So all bosons are symmetric under particle exchange. If you swap two bosons, then you'll find that their wave function doesn't change at all, not even sign, it's the same thing. But with fermions, when you swap the two, fermions are the anti-symmetric solution. When you swap the two fermions, then the wave function does change sign. So I'm going to ask the question, what happens if we try and put two particles in the same position? So I'm now going to say that x1 is equal to x2. We are going to put both particles in exactly the same position. What is going to happen in both case 1 and 2? Well, let's have a look at bosons. So let's substitute in our wave function, so psi x1, x2. This is going to now become psi of x1, x1. So x2 is equal to x1. The wave function is going to become psi of x1 and x1. So what happens when we do a particle exchange? Well, psi x1, x1 is equal, for the case of bosons, psi x1 is going to go to psi x1, x1 under the particle exchange, plus psi x1, x1. So yeah, we've literally just written that two things are equal to each other. No great insights right there. Nothing suspicious. But what happens for the other case? So let's try this for fermions. So psi x1, what it would be before, psi x1, x2 equals minus psi x2, x1. Psi x1, x1 is now going to become minus psi x1, x1. Now, if we just cancel both sides of this equation, which isn't mathematically great, then you can see that 1 equals minus 1, and so we have a paradox. So fermions, if we let x1 equal x2, we do not get a valid solution. So this is crucial. This is absolutely paramount to basically entire field of chemistry. This is where chemistry inherently comes from. Just this one little mathematical detail right here. So what is the solution to this? Well, the only valid solution for psi is that psi equals 0, because that's the only way that we're going to make this equation work right here. Psi has to be equal to 0. So what does that mean? That basically means that if psi is 0, then the probability is 0 of finding both particles in the exact same position. And this leads to the Pauli exclusion principle. This is what it's saying. It is saying that you cannot put two particles in the exact same position. Or more generally, it's saying that you cannot put two fermions in the same quantum mechanical state. That's what the Pauli exclusion principle is saying, because you otherwise end up with this weird equality right here that is seemingly a paradox, which is saying 1 equals minus 1. So that is not allowed. You cannot put two fermions in the exact same quantum state. Now, this isn't true at all for bosons. This was completely fine. You can have as many bosons as you want in the same quantum state. This is actually something that leads to Bose-Einstein condensation, which is a thing that's coming up very, very soon. But yeah, it does not, you cannot put two particles in the same quantum state, which is the Pauli exclusion principle. And the reason this leads to basically the entire field of chemistry is because you have electrons, which are fermions, that are in discrete energy levels. So you have an electron in this kind of state, and then you have an electron in this state, and then they fill up progressively, which basically gives rise to the entire structure of the atom, just from this right here. And it's the structure of the atom which basically determines how chemistry works, really, because the interaction between atoms of different structures therefore gives rise to chemistry. So that's the underlying thing. The Pauli exclusion principle can therefore explain chemistry, but then even go on to explain things like biology and stuff. So it comes from a very interesting mathematical principle. The other thing about these two different types of particles is that you can have what's known as positive correlations and negative correlations. Because bosons can occupy the same state, then there is nothing wrong with bosons sort of clumping together, all in like a kind of clumpy cloud. They like to kind of attract each other, if you like. But with fermions, because they have to be in this discrete positions all the time, then they actually exhibit kind of negative correlations, which is basically them avoiding each other. You can kind of think of bosons as being friendly, and you can think of fermions as being social distancing things. They like to be socially distant from other fermions. So now let's kind of bring this back to thermodynamics a little bit. And what I'm going to now try and do is I'm now going to try and derive an alternative form of the Maxwell-Boltzmann distribution, but instead for a classical distinguishable particles, I'm going to do this now for quantum indistinguishable particles. And what I'm going to do is I'm going to start with the formula that I used a couple of videos ago, which was the grand potential, omega, is equal to minus kBt times the log of the Landau partition function, which is this right here. If you haven't seen this video, then maybe go back to one of my previous videos. This term right here is the grand potential, which is a thermodynamic potential, which is good for situations in which the particle number changes. And this function right here is the Landau partition function, which is similar to the single particle partition function. However, it also accounts for the fluctuating particle number. Now, if I substitute in what L actually is, I get omega is kBt times the log of the sum over states of e to the minus epsilon minus mu over kBt. Now, this is for single particles, but of course we have a whole gas of particles, so we're going to multiply this by n right there. So we're going to sum over the particle occupancy number, which is what the Landau partition function does, and it sums over here, and it goes through each state, and there's like how many particles are in each state, and so you get one term for each state. So let's consider the example we have for fermions. Now, this is the slightly easier example because we said just a few minutes ago that fermions can only have occupancies of 0 or 1. You cannot have a doubly occupied state, you can't have a triple occupied state. It has to be either 0 or 1, which is going to make this summation pretty straightforward. It's just going to have two terms. It's going to have the 0 term and it's going to have the 1 term. So let's actually go ahead and evaluate the summation over particle occupancies. So we are going to get the first term, which is when nk is equal to 0. So if nk is equal to 0, then the whole term in the exponential is equal to 0, and e to the 0 is just 1. So the first term is just going to be 1. So no problems there. Plus our second term, which is when nk is equal to 1. So we're going to get plus e to the minus epsilon minus mu over kBt. And then the sum's just going to end. It's going to end right there because we can't have more than one particle in the same state right there. That is our Landau potential for this fermionic gas. So now what we're going to try and do is we're going to try and get from the magic box relations that I talked about in a previous video, we are going to now try and get the average occupancy of a state. And to get this, we actually differentiate the Landau potential with respect to the chemical potential. So the chemical potential, if we remember, we kind of see this as like the capability for new particles to kind of either flow in or flow out. That's basically what the chemical potential is. And if we differentiate the Landau function with respect to the chemical potential, we actually get the average occupancy of a single particle state. So I should just denote that it's a single particle state, I should be substituting everything with K right there. And this isn't quite true, there is in fact a minus sign on the front right there. So that basically just means differentiating this omega function right there. So what are we going to get? Well, both minus signs are going to cancel because we have a minus here and a minus here. This is going to be just kBt, which is a constant. T is a constant in this situation because we're only differentiating with respect to chemical potential. And how do we differentiate this log function? Well, we know that d by dx of log x is just 1 over x. So we can use that combined with the chain rule and differentiate this log function right here. So we're going to get 1 over whatever's in this log term right here. So we're just going to put all this in the denominator. We're going to get 1 plus e to the minus epsilon minus mu over kbt, multiplied by the inside derivative of this right here. So the 1 is just going to go, and now we just got to differentiate this bit right here. Now, it's kind of easier to do this if you separate out the exponential, because of course it's got epsilon minus mu. So if we actually separate that out, we're going to get e to the minus epsilon on kbt multiplied by e to the mu over kbt, because those two minus signs are going to cancel out when we expand the exponential. So we're just differentiating that basically, and hopefully you guys can see that this has no mu in it, so it's just a constant. So this is going to come out the front, and now we're just differentiating an exponential. So what's the factor that we have to multiply? Again, we're doing another chain rule. We have a 1 over kbt factor right here. So we have kbt, and we're going to divide everything by kbt, and we're going to get e to the mu over kbt. So a bit of complex derivatives right there. But as you guys can see, the kbt's will cancel out, and we can refactor this right here into what it was. So we're going to get e to the minus epsilon minus mu over kbt, all divided by 1 plus e to the minus epsilon minus mu over kbt. And just a quick note, the minus sign right here out the front is applying to the entire fraction within the exponential. It's not minus epsilon minus mu, it's applying to the whole thing. So that's what it is right there. And as one final step, I'm going to multiply the entire fraction by e to the plus epsilon minus mu over kbt. And what I'm going to get when I do that is that e to the plus something multiplied by e to the minus something is just 1. So that term's just going to become 1. And then for the denominator, this 1 is just going to become e to the epsilon minus mu over kbt. And then this term right here is also going to become 1. And there we go. This is what's known as the Fermi-Dirac distribution function. So this is telling us what the average occupancy of a certain energy level is at a given temperature. So it's very similar to the Maxwell-Boltzmann distribution. So let's repeat the whole process, but now we're going to do the same thing for bosons. And we're going to firstly calculate the Landau potential, and then we're going to differentiate that to get the average state occupancy. So starting again, we're going to get omega k equals minus kbt times the log of the partition function. And we're going to do the same substitution. We're going to sub in what L is, or fancy script L, I think it technically is. And we're going to get e to the minus epsilon minus mu over kbt, all summed. And now we are just going to do what we did before. And now just to put in what we're actually summing over. So I'm going to rewrite this, but just say that we are actually going to be summing over from a 0 occupancy to, in theory, you could have an infinitely occupied state, in theory. E to the minus epsilon minus mu over kbt times the state occupancy right there, nk. So now we're going to make the substitution that x is equal to e to the minus epsilon minus mu over kbt. Now we're going to substitute that into our formula for omega. So omega equals minus kBt times the log of the sum, which is nk equals 0 from infinity. And instead of e, we're going to now write x. And of course, using the law of the separation of exponentials, we can just write x to the power of nk right here. So that is using e to the a times b equals e to the a all to the power of b right there, just so we're clear. So now we've got to evaluate the sum. This is a well-known mathematical sum that has been studied quite a lot in maths, and it actually has a very simple form when you evaluate it. So the sum going from 0 to infinity of just x to the n, so n equals 0 to infinity, x to the n, I won't bother writing the k, this is just in terms of pure maths right here, is equal to 1 over 1 minus x. Now this is a very well-known sum identity. This, if you want a derivation of this, go check it out on YouTube. I'm sure there's a whole bunch of material that just easily derives it. It's very easy to derive that, but it's a very well-known summation result. So now we're going to just substitute that in to the formula for omega. We're going to get minus kBt times the log of 1 over 1 minus x right here. So now what I'm going to do is I'm now going to use one of the log laws just to invert this fraction right here. So if we use the log of 1 over a equals minus the log of a, this is basically a well-known log law. Hopefully you guys all know that and are familiar with it. Then basically this is just going to mean we're going to swap out the minus sign right here, and the term inside the log is just going to be 1 minus x right there. So that's kind of a bit nicer, looks a little bit neater. And finally, we're just going to swap out the x for what x actually is, which is e to the minus epsilon minus mu over kBt. So that is our omega function. And what we're going to do now is exactly the same as before. We're going to differentiate to get the average occupancy. So our average occupancy n is the derivative, or minus the derivative, of omega with respect to the chemical potential right there. So just like how it was before. So when we do this derivative again, the kBt is going to be a constant, so we're not really going to care about that. And again, we're differentiating a log function, so we're going to get a denominator of 1 minus e to the minus epsilon minus mu over kBt. So that's no different. And now we're going to multiply by the inside derivative of this right here. So like we did before, we're going to get a 1 over kBt factor, except this time we're going to have a minus sign right there. So there's going to be a minus e to the minus epsilon minus mu over kBt, because of course this time we actually have a minus sign. So the kBt's are going to cancel as before, and there is a minus sign from this definition right here, so these two minus signs are also going to cancel. So we're going to get e to the minus epsilon minus mu over kBt, all divided by 1 minus e to the minus epsilon minus mu over kBt. Now we're going to do exactly what we did before and just multiply everything through by e to the plus whatever's in this argument right here. That's going to be e to the 0, which is just 1, divided by e to the minus epsilon minus mu over kBt minus 1. That is nk. And that is, you'll be pleased to hear, this is the result for bosons, which is known as the Bose-Einstein distribution. So let's have a look at both distributions, because Aren't they just exactly the same? Well, not quite. This one right here, as we can see, is e to the epsilon minus mu over kBt minus 1, whereas the other one is plus 1. Now that little minus sign, that little difference in whether it's plus or minus, is the reason that we get this entirely different two types of particles in the universe. And actually, when we graph these functions, they do look very, very different. So let's first of all graph the Fermions function, which is the Fermi-Dirac distribution. When we graph that, we're going to get a curve that looks a little bit like this. So this is a curve that actually is quite familiar. It's called a logistic curve. It's actually reversed in the horizontal orientation. So it actually starts at the maximum and then gradually becomes zero asymptotically. So that's the Fermi-Dirac distribution. So it's a function of energy, and this is the average state occupancy. And as you can see, with increasing energy, the average state occupancy decreases, which is kind of what you'd expect. You know, and particles are more likely to occupy lower states. But of course, it's different to the Maxwell-Boltzmann distribution, which was just a exponential like that. But for the other one, distribution is the Bose-Einstein distribution. It looks very similar to the Maxwell-Boltzmann distribution, but it is slightly different. It will give you a slightly different value, particularly for low energies, and it won't, in fact, quite be the same. So just showing this mathematically, if the chemical potential in our dilute limit approximation, if the modulus of the chemical potential is much, much greater than the thermal energy, which of course was the case for a classical gas, then what do we get? Well, we find that in the limits, the term inside both exponentials becomes very, very large. So mu over kBt is very, very, very large. And so this is going to become a highly dominant term for large chemical potentials. And so what happens when you have a large number raised to the power of e? So, well, e to the large number, it's going to be a very, very, very large number because it's being raised to by the power of e. So it's going to get really big, and it's going to completely overshadow this one we have right here. So whether it's plus 1 in the Fermi case or whether it's minus 1 in the Bose case is not going to matter for the physics of the system. E to the large number is basically going to equal e to the large number. Adding or subtracting 1 won't make a difference, proportionally speaking. So what are both distributions going to tend to? Well, we're just literally going to get 1 over e to the minus epsilon minus mu over kBt, which, if we do that, is simply e to the epsilon minus mu over kBt. Sorry, there is a mistake right there. That should be a plus e to the plus epsilon minus mu over kBt for the Bose-Einstein distribution. So we're just going to get a e to the minus, oh yeah, so 1 over minus is that. You've got to be careful. So we're going to get basically e to the minus something, which is the Maxwell-Boltzmann distribution. Just that right there, e to the minus epsilon minus mu over kBt. So that's exactly what we expect for the dilute limit. When mu becomes very, very much larger than the thermal energy, then we simply expect the Maxwell-Boltzmann distribution. But when mu isn't larger than the thermal energy, then we get this kind of quantum regime. And this kind of relates to the thermal wavelength that I was talking about in the last video. The thermal wavelength is to do with the temperature and the concentration, and at these limits you actually get into the quantum regime for gases. And these are the two distributions that are governing. So this one is the Fermi-Dirac distribution. This one is the Bose-Einstein distribution, and this one is the Fermi-Dirac distribution. And both of them describe fermions and bosons, which are both halves of the universe. So nice, we have derived both distribution functions. They're going to come up a lot. They are very, very useful to know. But I hope you guys can understand where they come from now. They fundamentally come from this idea of particles being distinguishable versus non-distinguishable. And yeah, we are going to be using these in the upcoming videos. In the next video, we're going to be talking about Bose-Einstein condensation, which is really cool. So yeah, we're also going to be talking about applications of the Fermi distribution as well. It's very, very important in solid state physics, which is a very hard area to understand. And so I'm going to do my best to try and make that as clear as possible. So yeah, see you guys in the next video.